Pinch pressure on a plasma. A plasma is a gas of ionized charged particles. When plasma is in motion, magnetic effects squeeze its volume, inducing inward pressure known as a pinch. Consider a cylindrical tube of plasma with radius capital R and length capital L, moving with velocity v along its axis. If there are n ions per unit volume and each ion has charge Q, we can determine the pressure felt by the walls of the cylinder. Part A. What is the volume charge density ρ in terms of n and Q? So here is our cylinder filled with these ionized charged particles, the plasma. The cylinder is moving with velocity v along its axis. Let's say it's moving down. We have radius capital R and length capital L. And we are given that there are n ions per unit volume. So what is the charge density? Now, the charge density is charge per volume. The total charge per volume. Now, we know the charge per ion. Each ion has charge Q. Each ion has charge Q, so this is given to us. And n ions per unit volume. So using this information, if I multiply charge per ion with the number of ions per volume, I will obtain the charge density. So the charge density ρ will be Q, the charge per ion, multiplied by number of charges per volume. So number of charges times number of ions gives us total charge. Then it is per volume. So this is going to be our charge density. So that's the answer to part A of this question. Part B. The thickness of the cylinder surface is n to the power minus 1/3. What is the surface charge density sigma in terms of n and Q? The thickness of the surface is n to minus 1/3. What is the surface charge density? So this is part B. So we can calculate the volume of the surface. By surface, we mean a thin shell here. So it's the volume of the surface, that's why we are using these quotation marks, is its thickness. Thickness is given as n to minus 1/3 multiplied by the circumference. The surface area basically is circumference 2 pi r multiplied with height. Height is capital L. So if I multiply 2 pi r, the circumference, with the height capital L, I will find the surface area. So surface area multiplied with the thickness will give me the volume of this shell. The volume of this shell, V sub s, is 2 pi capital R L n to the power minus 1/3. Because the surface area is 2 pi capital R times L. Okay, so what is the surface charge density, charge per area? Well, it's the total number of charges, which is the charge density rho, volume charge density rho, multiplied by the volume, that's the total number of charges, divided by the area, which is 2 pi capital R L. So rho we calculated as Q times N, so N Q. Then we have 2 pi capital R L N to the power minus 1/3, that's the volume of the surface, divided by 2 pi capital R L. 2 pi capital R L's will cancel, and we will obtain the surface charge density, sigma, to be, because I have n to minus 1/3 and n to 2/3 times q. That's the surface charge density, sigma. Okay, so let's move on to part C. The current density inside the cylinder is rho, the charge density, multiplied by velocity v. Use this result along with Ampere's law to determine the magnetic field on the surface of the cylinder. Denote the circumferential unit vector as phi hat. Okay, so for this part, the first thing we do is we note that the current density J is equal to charge density rho multiplied by velocity. It's a dq dt per area, right? So this is number of charges per volume. Volume multiplied by displacement gives us per area. Then we have the number of charges per unit time, so Q over T, so we obtain current density. So dimensionally, this makes sense. Now we define this angle phi for the circumferential vector, angular displacement phi, and we have the current density in this direction because the velocity is in this direction. So the current density is in the direction of the velocity. Now, using Ampere's law with the right-hand rule, the right-hand thumb points in the direction of the current. The four fingers of the right hand curl in the direction of the magnetic field, which gives us this sense of rotation, the clockwise sense for the magnetic field at the surface of this cylinder. Now, if I write Ampere's law, closed path integral B dot dl, this is equal to, for the surface, I have magnetic field, a constant on the surface, multiplied with 2 pi r, because the dl for this calculation, this is the dl. dl and magnetic field are in the same direction. This is mu 0 times current enclosed, mu 0 permeability of free space times current enclosed. What is the current passing through this loop? It is J times the cross-sectional area pi r square. So this is mu 0 J times the area. So I find that this is B times 2 pi capital R, which is equal to mu 0. The current density is rho V, and I have pi capital R square for the area. So pi's will cancel. This R will get rid of this R, and I will find the magnitude of the magnetic field to be mu 0 rho VR divided by 2. Now, I know that rho is equal to NQ, so I can substitute here mu 0 NQ VR divided by 2, that's the magnitude. So defining this phi hat direction basically in the clockwise rotation sense, I can write the magnetic field vector as its magnitude mu 0 n q v capital R divided by 2 in phi hat direction. That's the magnetic field at the surface. All right, so let's take a look at part D. The width of a differential strip of surface current is R d phi. What is the differential current di surface that flows along the strip? Okay, so we have R d phi basically is this, when I define this angle phi here, R d phi is this arc length. So the area of the surface is R d phi, cross-sectional area, R d phi times n to minus 1/3. That's my differential area here. Differential area is capital R n to minus 1/3 d phi for this strip. And this is the top view. So I'm looking at this from the top. So basically I see this shell. What is di surface? The current, the surface current is the current density J multiplied by dA, because we have a uniform surface, uniform current density. So I can calculate di surface to be the current density rho, which is nq multiplied by v. The area is capital R n to the minus 1/3 d phi. So this is going to be, because I have n to minus 1/3 and n to 2/3, the surface current di surface is equal to q capital R n to the power 2/3 v d phi. Now you can notice that from part B, the surface charge density was n to 2/3 q. So this is actually sigma times r v d phi. So sigma v times r d phi, which is going to be the surface current. But let's give the answer this way because we were told to do so, I think. So we're trying to find in terms of nq. Sigma is not given to us. Okay, now part E. What differential force is felt by this strip due to the magnetic field generated by the volume current? So it's going to feel differential force. This current will interact with the magnetic field and will feel a differential force. So what is that differential force? This is part E. Differential force, dF, for a current carrying conductor in a magnetic field, it's going to be di surface L cross product with a magnetic field, IL cross B. Now, what is the direction of L vector here? L is in minus k hat direction. Why is it in minus k hat direction? Because the current is in the downward direction. So basically, I have assumed that, so this is the top view, so Z is coming up, that's k hat direction. So because it's down, the current is going down, its L vector is in minus k hat direction. I know the direction of the magnetic field. Magnetic field has magnitude B in phi hat direction. Therefore, what is L cross with B? It is BL minus K hat cross with phi hat. Okay, so if you look at this top view here, this is my r hat direction, the radially outward unit vector. This is my phi hat direction. Now you can see if I have phi hat cross with r hat, so your right hand forefingers point down, phi hat cross with r hat, curl towards r hat, that gives me k hat. So phi hat cross r hat is k hat, or r hat cross phi hat is minus k hat. So from these cyclic permutations, I can see what is going on. R hat cross phi hat is minus k hat. Phi hat cross k hat, that's the negative direction, is minus r hat. And k hat cross phi hat, k hat cross phi hat is plus r hat. Therefore, if you have minus k hat cross phi hat, it is pointing radially inward. It's in minus r hat direction. Okay, so after finding that this vector points in minus r hat direction, it's radially inward, I can write the differential force. Differential force dF is di surface. I know what di surface is. QR n to 2/3 v d phi. So Q capital R n to 2/3 v d phi. Then I have L cross B, L times B. B I have calculated in part C, mu 0 n q v r over 2, mu 0 n q v capital R over 2. So that's going to give me the magnitude of the differential force. So this gives me dF. This gives me dF to be mu 0 over 2 n to the power 2/3 and n to 5/3 n to 5/3. Then I have q and q, so it's going to be q squared. Then I have two v's, v here, so it's going to be v squared. Two r's, r here, it's going to be r squared, and there is a single L. So this is the magnitude of the force felt by this differential current segment, and it's basically pointing radially inward. It's towards the center. Let's move on to part F. Integrate to determine the total force on the walls of the cylinder, then divide by the wall area to obtain the pressure in terms of NQ capital R and V. What is the total force? Well, each current segment feels this force, so if I integrate this over all angles phi from 0 to 2 pi dF, I will find the total force. That's just going to be, because there is no phi here, this is going to be an integral. There is a d phi here remaining. So integral over phi, that will give me just a factor of 2 pi. So this will be mu 0 over 2 n to 5/3 q square v square r square L times 2 pi. So the 2's will cancel. So I will obtain the total force. The total force felt by the plasma, mu 0 pi n to 5/3 q square v square r square capital L. And what is the pressure? Pressure is force per area. Force per area. What is this area? It's the sidewall area. The force is radially inward, so the force we feel per area is perpendicular area is the sidewall area. So I'm going to divide this force by 2 pi r capital L. All right, the force is pointing radially inward. The perpendicular area it sees is the surface area of the cylinder. Therefore, I will find the pressure to be mu 0 over 2. The pi will disappear, right? So there's no pi. And then I will have n to the 5/3, n to the 5/3, q square, v square. There's r square, L divided by RL, that gives me R. So the pressure is given by this expression. Okay, so finally, in part G of this problem, I want to give it some numbers. If a plasma cylinder with radius 2 centimeters has a charge density of 8 times 10 to 16 ions per centimeter cube, where each ion has a charge of electron charge 1.6 10 to minus 19 coulombs and is moving axially with a speed of 20 meters per second, what is the pinch pressure? Capital R is 2 centimeters, N is 8.0 10 to 16 ions per centimeter cube. The electron charge is 1.6 10 to minus 19 coulombs. The axial speed is 20 meters per second. Then the pressure is mu 0 over 2. Mu 0 is 4 pi 10 to minus 7 Henry per meter divided by 2. Then I have N, 8 times 10 to 16 ions per centimeter cube. 1 centimeter is 10 to minus 2 meters. So this is divided by 10 to minus 6 meter cube to the power 5/3. The electron charge 1.6 10 to minus 19 coulombs squared. And then I have V squared, which is 400, times R. R is 2 centimeters, 2 10 to minus 2 meters. This is going to give me the pressure in SI units, 1.9 times 10 to minus 5 pascals. All right, so that's going to be the pressure we will see. So in this problem, we talked about plasma inside a cylinder moving axially with velocity v in the downward direction. If we have n ions per unit volume and they each have a charge q, n times q is the volume charge density. If the shell of this cylinder has a thickness n to minus 1/3, then we have the surface volume, surface area times the thickness, and the total charge, rho times the volume of the surface divided by its area gives us the surface charge density, n to 2/3 q. The current density is rho times v, the charge density multiplied by the velocity. Using Ampere's law for this path, using the right-hand rule, we find that if the current is pointing down, our thumb points down, the four fingers of the right hand curl in this direction, which I define to be phi hat direction. B times 2 pi r, B integral B dot dl is mu 0 times current enclosed, which is J times the cross-sectional area A here, which is going to be rho v times pi r square. From this I can calculate the magnetic field in phi hat direction. So in part D, the width of a differential strip of surface current is r d phi. What is the differential current? The width of this differential surface is r d phi, and its thickness is n to minus 1/3. So di surface is j times dA. Now we already know what j is, rho times v and q times v multiplied by dA. Well, that is r d phi multiplied by n to minus 1/3. So we can calculate the surface current that flows through this shell. And the force it feels is di L cross B. L cross B I have found, noting L is in minus k hat direction of the current, B is in phi hat direction. Using the right hand rule, you can find minus k hat cross with phi hat. If your right hand forefingers point into the page, curl them towards phi hat direction, which is pointing down here, the thumb points radially inward. So this is in minus r hat direction. So BL multiplied by the di surface we calculated, we find the force. If you integrate this over all possible phi's from 0 to 2 pi, that's basically multiplying this by 2 pi and dividing it by the surface area, because the force is pointing radially inward, the cross-sectional area is the surface area, 2 pi rl. We obtain the pressure, and we can substitute some numbers here to find the pressure in pascals.